In this session, I'll be talking about planning 2K DOEs. That's 2 levels for K number of factors design of experiments. So at the end of this session, you'll be able to set up a DOE, determine factors, levels, and resolution for a planned DOE, describe blocking, experiment, randomization, and curve check for a DOE. So this is where we're at in the overall roadmap. And these are the drill downs that I'll be talking about. There's further drill downs in the project, Lean Six Sigma project execution guide. So again, why are we doing this? Well, 30,000 foot level report out indicates that we need to go in and make an improvement. So we're trying to identify what we should do to improve. So we want to run hypothesis tests in the region of stability. We can use wisdom of the organization thoughts to help us determine where we feel focus improvement efforts. And then we can use also this to see a quantification of what benefits we made from our improvement efforts. So again, we're starting with a big picture 30,000 foot level. We're indicating we got a not as good a conformance as we like. It pulls for creation of projects. So now the idea is we do a DOE and then we can see the benefits of what we've done. So the mechanics of a DOE is not very difficult. However, you spend much time and resources can be wasted if it's not set up wisely. The chapter that we're described here, it's going to be covering a lot of those considerations that you should be making when you set up a DOE. So we're going to be focusing on fractional factorial experiments rather than a full factorial experiment when we execute these DOEs. When designing a DOE, it's most important that everybody agrees what we're going to do and we're not going to do, what we can hold steady or control it, and what we're not going to change. So brainstorming a cause and effect diagram can be helpful in determining what we might look at and the change that we might make to various factors to improve the overall response. Also, passive analysis from for this particular metric can help us gain insight to how we choose factors and levels of the factors. So consider a single unreplicated 2K DOEs, which is sometimes called the unreplicated factorials. That's what I'm going to really be suggesting. There's going to be no internal estimate for error. The analysis of this unreplicated trials, we're going to be using the high-level order interactions to determine what that estimate is, and we're addressing significance. Now, the reason for this is what's called sparsity effect. So basically, we don't have, in the real world, everything being significant. So the higher level interactions, those are things we're not going to be considered significant, but the effects from those can be used in an estimate for error. You can use the multiple experiment strategies for detecting errors, interactions. So now you start with a high level and then you do another experiment to go in and do further refinements. But that's not necessarily always with a case, as I described some other alternatives in the chapters of the book. So it's really important, rather than just getting a large sample, is do everything you can to get the lowest possible measurement error. That's what everything is assessed against. So if you got a low experimental error, then the thing is we can detect differences between the high and low levels better if you got low experimental error. So for an individual experiment, there's trade-offs typically need to be made for the number of factors, trials, resolution, and possible follow-up experiments. So we really need to have good front-up work on a design of experiment to decide what we want to do. Because a lot of times they're fairly expensive, and it can take a lot of resources, and we want to do it right the first time. So sometimes we look at collinearity or nonlinearity when we consider 2 levels. Well, that's what we need to also consider when we pick the two levels. We don't want to have them so far apart that we've got nonlinearity issues. So we have to really address that. And the way we can do that is we could add curvature checks. So we can add other factors that's halfway through it and in that and see if there's some curvature. Because when we do 2 to the k, we got two levels. We're assuming a linear relationship between the high and low values. So this would be a means that we could check for curvature and then make appropriate adjustments in a follow-up experiment. So full level designs are used to assess all possible combinations. Information is contained about all possible interactions. For a full factorial, for example, we'd have 7 factors, and we could have 2 to the 7th, that's 128 trials. But in reality, all these factors and interactions, just it's not in the real world, they wouldn't be significant. So resolution 5 design evaluates the main effects and 2-factor interactions independently. Resolution 4 design evaluates the main effects and which is compounded with the 2-factor interaction. Resolution 3 design evaluates the main effects which are compounded with 2-factor interactions. Tables M1 to M5 can be used to test alternatives for these situations. So we got something else to consider is blocking or randomization. Sometimes what we'll have is we need to do blocking. For example, maybe half of our trials could be done on one day and the other half on the other day. Well, the question is, which trials do we run on day 1 and which trials on day 2? Now we can block it on day 1 and day 2, or we can just consider their randomization. So let's consider that there was a difference between day 1 and day 2. The blocking would tend to cancel it out, so that wouldn't affect the other factors in the experiment. And so you would minimize the experimental error. But if they were randomized and you truly had a difference between day 1 and day 2, that's going to increase your experimental error. So blocking should be considered as part of an experiment that's getting conducted. Curvature check, when you have curvature check, you're looking at the high and low level for a particular factor, and what we're assuming when it's 2 to the k, that's linear relationship. But if we ran another trial halfway between them, then we'd expect not to get curvature. So that's basically what a curvature check is, and we need to consider that part of our experiment planning. So in this module, we talked about DOE setups, talked about factors, levels, and resolutions, and we also talked about blocking, randomizations, and curvature check.